Good afternoon, everyone. Welcome back to NPTL tutorial session of the course Classics in Total Synthesis Part 1, which is taken by Professor Krishna P. Kaliappan from Indian Institute of Technology, Bombay. And today is our ninth tutorial session, and let's start the discussion. Myself, Sreelekshmi, I am a PMRF research fellow under Professor Krishna P. Kaliappan. I am doing my PhD under organic chemistry. I am a third year student. So let me share my screen first. Okay. So yes, I hope screen is visible to you. So as in the previous tutorial sessions, I hope you have gone through that. We have already taken about 8 tutorial sessions so far. So as in the previous sessions, we will be discussing the assignment questions in the beginning. There will be 10 questions. So one of the week's assignment, we will discuss all the questions and the related mechanisms. Then we will have a brief discussion on the last week's lectures. That is, I think, week 9 lectures. So five lectures were there in total. So we will have a brief discussion on that lectures, and then we will move on to the discussion of some mechanisms of the reactions that we came across while attending those lectures or while having the discussion. So that will be the basic idea of today's tutorial as well. So as usual, we will begin with the discussion on assignment questions. Okay, so today we will be discussing week 7 assignment. Till until the last lecture. In the last lecture also we had a discussion on the week 6 assignment. So as a continuation, today we will be discussing this week 7 assignment. So directly we will move to the first question, that is, identify the major product in the following transformation. So here one reaction is given, that is, this particular compound on treatment with dbu in toluene, what will be the major product in this transformation? So that is the first question for this assignment. So upon treatment with dbu, what can happen in this reaction? As you can see, the four options here, the first option is like cyclization, an additional 5 membered ring is forming, and the second option is like isomerization, and the third option is like, again, an additional ring is forming, but the difference between option A and option C is that the presence of this double bond in option C, as well as the stereochemistry of this particular ester group. Then in option D, as we can see here, this alkene is present, but the stereochemistry of this ester is different from that of option C. So that are the four options given here. So what will be the major product in this transformation? So I'll give you a couple of minutes time to think about this mechanism and the major product as well. So what will be the role of DBU in particular? Okay. So The correct answer for this question is option D, that is this one. So what is basically happening in this reaction is given here. So as you know, first on treatment with DBU, I have given the first intermediate forming in this reaction. So this proton will be abstracted by this DBU, and as a result this double bond will shift to this position. So isomerization of the double bond will be the first step when we are treating it with the DBU. So this will be the corresponding intermediate forming. And in the next step, what will be happening is the O lone pair of oxygen will attack this carbon attached to this bromine center, and this bromine will get eliminated. Then in the next step, again this double bond will migrate to here. Like again, base will abstract the proton from here, and this double bond will migrate to this position. So this will be again, because it is more stable alpha beta conjugated unsaturated ketone. So for the formation of that alpha beta unsaturated ketone, this double bond will be migrating again to this position. That is basically this proton will be migrating from this particular center to this particular center. So we will get this option D as the major product. So I hope it is clear. Once again, I will tell what is happening in this mechanism. So first, on treatment with DBU, first thing which is happening is DBU will abstract this proton, and this double bond will shift to here to give this intermediate. And in the following sequence, this lone pair of oxygen will attack at the carbon center, that is second position of this carbonyl group, and bromine will get eliminated to get this furan type of ring, 5 membered ring. An additional 5 membered ring will be resulted. Then this double bond will get again isomerized to form this alpha beta unsaturated ketone as a major product. So the correct answer will be option D. So that is the first question. Now moving to the second question, what is the major product formed in the following transformation? So this compound upon treatment with this alcohol, this particular alcohol, that is methane sulfonic, not alcohol, it is acid actually, like TSOH, paratoluene sulfonic acid, this is methane sulfonic acid, and P2O5, that is phosphorus pentoxide. What will be the product obtained in this transformation? So as we can see in the option 1 and option 2, there is an additional 6 member ring formation, and option C, there is a methyl group which is connected to an additional furan type of furan type of ring, and in option D also another 5 member ring is forming. So basically in this reaction, as we can see, one extra ring is getting formed from the starting material. So what is the possibility for this reaction, and what will be the corresponding mechanism? Okay, so here the correct answer is option B, and what is happening here is simply this. It is like Eaton's reagent, so it is helping in the cyclization. So this will be attacking either at this, like it is like Friedel-Crafts acylation, so it can happen either at this alpha position or at this uh, ortho position or at this para position. Since para positions will be more activated to this, that is to this hydroxyl group, considering this hydroxyl group, the para position of this hydroxyl group will be more activated than the corresponding ortho position. So the cyclization, Friedel-Crafts acylation or Friedel-Crafts cyclization will happen at this particular para position, and as a result we will be getting 1, 2, 3, 4, 5, 6. A 6 member ring will be forming. So that is the correct answer. Option B will be the correct answer for this question. That is, this is basically Friedel-Crafts acylation presence of this Eaton's reagent. So this two positions are available for that ortho to this hydroxyl group as well as para to this hydroxyl group. And as we know, due to this electron donating effect of this hydroxyl group, this para position would be more favored to this acylation or this cyclization rather than this ortho position. So this will be the major product, that is cyclization is happening at this para position, resulting in this 6 member ring, additional 6 member ring. So option B will be the major product in this transformation. Now moving to the next question, identify the major product in the following transformation. So this particular compound is treated with FeCl3, HCl and H2O, and in the second step it is treated with the sulfur dioxide, methanol and water. So what will be the major product in this reaction out of the four options given here? So as you can see here, option 1 correspond to this hydroxyl group, and this NH2 converted into this ketone, and aromatic ring also got uh, converted into this corresponding diketone. And in the second option we can see this NH2 has converted into this OH, and in option C, and like additional hydroxyl group has come at this position ortho to this hydroxyl group, and in option D this NH2 got eliminated and then OH is coming, hydroxyl group is coming at the position ortho to this O benzyl group. So what will be the transformation in this reaction in two steps? Okay, so here what is happening is first step, that is, this is the intermediate forming in the first step, or the product we are getting in the first step is this FeCl3 is oxidizing this both the ketone and amine as well as this aromatic ring into this diketo compound. So this will be the product. Then in the next step under SO2 Me methanol condition, we will be getting the aromatic ring intact, and this 1,2 diketone will be reduced to this diol. So that is what is happening in this reaction. In the first step we will get this diketone, and the second step we will get this diol. So this option A will be correct if only first option was there, that is FeCl3, HCl and H2O. But since we are treating it with this sulfur dioxide in methanol and water, it will get reduced as well. So the correct answer will be option B. So I hope it is clear. Now, moving to the next question, what is the major product formed in the reaction given below? So, this particular compound is treated with first MCPBA in DCM, and then this titanium tetraisopropoxide in benzene. So, what will be the product obtained after subjecting this starting material for these two steps? These two steps separately. So, what will be the product we will be getting in this reaction? So here, as we know, here there is an alkene present here. So what MCPBA will be doing, it will epoxidize this double bond. And since this alcohol is here, that alcohol will direct the epoxidation, and so epoxide will be forming in the same side of that of this hydroxyl group. So what we will be getting, this hydroxyl group having the same stereochemistry, this epoxide having the same stereochemistry as that of this hydroxyl group will be formed in the first step. And in the next step, what is happening is the epoxide will get opened, and that is, we can say from here, if it is pulling, and this, let me take my pen. So as we know, here one hydrogen will be there, so that will push, that will give its electron to this here, and as a result this epoxide will open, and here we will be getting that double bond. That epoxide will be converted into corresponding open product, that is alcohol, as a result of this treating it with titanium tetraisopropoxide. So we will be getting this corresponding diol with the double bond shifted to this position as a major product. So option C will be the major product in this reaction. So I hope it is clear. So what is happening in the first step on treatment with this MCPB and DCM, an epoxide will be forming, that is this product we will be getting, and the stereochemistry will be controlled by this directing group, that is alcohol present here. So epoxide will be formed in the same position as that of this hydroxyl group, because this oxygen lone pair will have the tendency to coordinate with this MCPBA. This will direct the epoxidation uh, in the same side as that of this hydroxyl group. So after getting this epoxide on treatment with this titanium isopropoxide, this epoxide will be opening, forming the alcohol at this particular position and double bond at this particular position. So we will be getting this option C as the major product. Now moving to the next question, which of the following reagents would carry out the following transformation? So here, as we can see here, it is like a new cycle is formed with this ring junction carbon and this carbonyl carbon. So which reagents can result in this following, in this given transformation? First option is first treating with this diisomethane, then this oxalyl chloride, and then this dirodium tetraacetate. And in option 2, first treating with this diisomethane, then with dirodium tetraacetate, and then with oxalyl chloride. Option C, first oxalyl chloride, then diisomethane, then dirodium tetraacetate, and in option D, oxalyl chloride, dirodium tetraacetate, and diisomethane. So just these four options have three steps: diisomethane, oxalyl chloride, and dirodium tetraacetate. But we have to identify the correct sequence of this particular reagent to help in this transformation. So what will be the correct sequence of these three reagents to be used to get this reaction? So here the correct sequence of reaction is first treating this compound with oxalyl chloride and then with diisomethane and then with dirhodium tetraacetate. So what will be happening when we are first treating with this particular compound with oxalyl chloride? Obviously this carboxylic acid will get activated and it will get converted into corresponding acid chloride. So we will be getting this compound as a major product. Then on treating this acid chloride with this diisomethane, we will get this particular diazo compound. And in the next step, while treating with this dirhodium tetraacetate, it will undergo a carbene formation. That is, particularly we can say a carbenoid will be forming with rhodium by the extrusion of this nitrogen, and that carbene will undergo reaction with this particular carbon. That is alpha, beta, gamma, delta. Delta ring will be forming. That is, it will result in the formation of 1, 2, 3, 4, 5. Right? 1, 2, 3, 4, 5. A 5-membered ring will be forming. So that will be the major product in this reaction that is given here. So from this compound to this compound for the particular transformation, first we have to activate this carboxylic acid to get this acid chloride, and then treating it with this diisomethane will give this diazo compound, and then we have to treat it with dirhodium tetraacetate so that it will undergo this carbenoid formation and subsequent the cyclization to get this product given here. So the correct answer will be option C. Now moving to the next question, which of the following reagents would carry out the following transformation? So as we can see, only change in the starting material from the product is just the stereochemistry of this hydroxyl group, where here it is beta and here it is alpha. That is, here it is above the plane and here it is below the plane. So first option is first treating with this methyl chloride triethylamine, and in second step H2O2. Then second option is first treating with tosyl chloride triethylamine and then with H2O2. Then the third option is first treating with this sodium hydroxide, and in the second step PPH3 dead and this carboxylic acid, benzoic acid. The last option is first treating with this PPH3 dead and this benzoic acid, and second step treating with the sodium hydroxide. So what will be the major product? Major product is already given. So what will be the corresponding reagents to carry out this transformation? That is just to invert the stereochemistry of the hydroxyl group. So as we know, for inverting the stereochemistry of a particular carbon center, the reaction which we have to carry out is Mitsunobu reaction. So that is what is happening here. First on treatment with this PPH3 dead than this benzoic acid. Here that particular, that is O C double bond or OH will be coming, but that particular group will be having inverted stereochemistry as that of this hydroxyl group, because Mitsunobu reaction is an SN2 reaction. Then on hydrolysis, that particular carboxylic acid will be converted into this alcohol with that particular our desired stereochemistry. So the correct option will be option 1, PPH3 dead benzoic acid, and the second step for acid hydrolysis, to get the corresponding alcohol we are treating it with sodium hydroxide. So this is the general mechanism for Mitsunobu reaction, which is a redox reaction. We have already discussed about this reaction in previous lectures as well. So that is this carboxylic acid and this alcohol in presence of this PPH3 and that we are getting, it is like a nucleophilic substitution. That's R1. Here this nucleophile R1 will get attacked to this particular, or this H will be replaced by this R1. So here also same thing is happening when we are treating with this particular alcohol with this benzoic acid. So mechanism, I am not going into the details before, we have already discussed. So first PPH3 will coordinate with this diad, and that diad nitrogen will abstract the proton and make our nucleophile. Then once the PPH3 will coordinate with the alcohol, this nucleophile, this O minus will attack our R1 and we will get a corresponding product, and PPH3PO will be the byproduct. So here what will be happening? Here this O C double bond or OH will be forming with, since we are using this corresponding benzoic acid. And when we are doing this hydrolysis with NaOH, that O C double bond or OH will cleave and this OH will be forming, but this O C double bond or OH will be having the opposite stereochemistry, because as we can see, this this attack is actually SN2, that is, yes, here this is first eliminating, and this on this alcohol, this is getting attacked in the inverted manner. It is basically an SN2 reaction. So we will be getting this option D as the correct answer. First Mitsunobu reaction followed by the ester hydrolysis. Now moving to the next question, that is seventh question. Identify the major product in the reaction given below. So this is also a two-step reaction sequence. First, we are treating this compound with this BH3 SME2, and in the second step, we are treating it with H2O2 and NaOH. So out of the three options given here, in the first option, second option, and third option, this particular alkene is converting into CH2OH, but differing in the corresponding stereochemistry. And in the third option, this is converting into CH2BH2. So what will be the major product formed in this reaction? So here, the major product obtained in this reaction is option D. So what is happening in this reaction is, first step, hydroboration will take place. That is, this particular double bond will react with this BH3 SME2, and this, to this position hydrogen will be attacked, and to this position boron will be attacked, and we will get this intermediate. That is, in the next step, what is happening is, this oxygen lone pairs will coordinate with this boron, which is electron deficient, and it will create a positive charge on this oxygen. Then this hydride shift will be taking place. That is, this hydrogen will get transferred into this position, and this double bond will stabilize this positive charge on this oxygen. Then by treating with this H2O2, it will get converted into corresponding this diode. So that is what is happening in this reaction. So the correct answer will be option D. And as we know, the stereochemistry will be directed by this particular angular methyl group. Since it is above the plane, this alkene reduction will give the compound in the below the plane. So that is what is happening in this reaction. First hydroboration, and then, like, basically it is hydroboration and oxidation. And correspondingly in the same pot, this double bond O is converting into OH by the transfer of this particular hydride into this carbon, and reducing this ketone as well. So hydroboration, oxidation of this double bond, and reduction of this ketone will be taking place by the sequence of this reaction, first treating with this boron reagent and then H2O2 NaOH. So the next reaction is, identify the major product in the following transformation. So this particular compound on treatment with samarium iodide in THF at 25 degrees Celsius, what will be the major product in this reaction? So as we can see in all the product, one additional ring is forming, but the ring size matters. So what is the possibility when we are treating this particular compound with samarium iodide in THF? So here the correct answer is option A, and this is happening in this reaction. So what is basically happening? This is attacking to here, and this oxygen lone pair will attack this carbonyl carbon, and one OMe will be eliminated. So that will result in the formation of one, two, three, four, five, six membered ring. Six, right? One, two, three, four, five. Okay, so this is happening like this. So this bond is getting attacked at this position, and this oxygen lone pair will attack this carbonyl carbon center. So it is like one, two, three, four, five. One, two, three, four, five. Two five-membered rings are forming. In addition to this, two five-membered rings already present here. That is one out of which one is a lactone ring, and this OMe will get eliminated. One OMe will get eliminated. So at the ring junction, we can see this isopropyl group is also present. That is, this will attack this carbonyl carbon, and this. So this double bond will attack this electrophilic carbonyl carbon, and this oxygen lone pairs will attack this carbonyl center, resulting in the elimination of one of the OMe group to form two five-membered rings in addition. So the correct answer will be option A. Now the next question is identify the major product of the following reaction. This compound on treatment with this particular chloromethyl ester in presence of this potassium tertiary butoxide in benzene, what will be the major product in this reaction? So here the correct answer will be option B. And what is happening? This potassium tertiary butoxide will abstract a proton from here, and that will create a negative charge at this position. And that negative charge will be attacking this carbonyl carbon center, and this oxygen will attack at this particular position, and the Cl minus will get eliminated. So what we will be getting, 1, 2, 3, an epoxide ring will be forming as shown in this reaction. So it is a named reaction which is known as Darson's reaction. Darson's reaction is basically a chemical reaction which is in which we are using a ketone or aldehyde. Here we have used a ketone with alpha haloester in the presence of a base, that is potassium tertiary butoxide, to form an alpha beta epoxy ester. So that from that it is clear that option B will be the correct answer. So alpha beta epoxy ester, which is also called glycidic ester. So the reaction mechanism is like that. This strong base is used to form a carbanion at the halogenated position, and because of this ester present here, this carbanion will be resonance stabilized enolate, which makes it relatively easy to form. So this nucleophilic structure, so this particular nucleophilic structure attacks other carbonyl compound, forming a new carbon-carbon bond. These first two steps are similar to a base catalyzed aldol reaction. Then the oxygen anion in this aldol product then does an intramolecular SN to attack on the formerly nucleophilic halide bearing position, displacing this halide to form an epoxide. So this reaction sequence is thus a condensation reaction since there is net loss of HCl when these two reactant molecules join. So the primary role of this ester is to enable the initial deprotection to occur, and other carbonyl functional groups can be used instead. So that is the mechanism of this reaction. This is a named reaction which is known as Darson's reaction. Now moving to the last question of this assignment. Identify the major product in this reaction. So this particular compound is treated with this AIBN, isobutyronitride, bis-isobutyronitride, and tributyl tin hydride in toluene heating. What will be the major product out of this four options given here? So here, this is basically a free radical cyclization reaction. So this is happening on treatment with this isobutronitrile and tributyl tinhydride. This OB said like homolytic cleavage will be taking place at this position, and this bond will cleave homolytically, and here we will get this nitrogen radical. Then in the next step, this alkene bond will be cleaved homolytically, and we will get one radical here and one radical here. So these two radical will be combining to form this carbon nitrogen bond. And in the next step, what is happening is this this one radical is here. So what is happening here is this bond will be cleaved. So one radical will be here and one radical will be here. Because of this, this is a four membered ring, so it will be considerably unstable. So now these two radicals will combine to give an alkene here, and this radical will be quenched by the corresponding hydrogen radical from this tributyl tinhydride. So this will be the product. Option C will be the product in this reaction. So that is happening. First, this NO bond will be cleaving homolytically to get this radical here, which will attack on this alkene to form a radical at this carbon center. Then this four membered ring will be opening homolytically to form a radical here, and so that will combine with this radical to form this alkene. And this particular radical at this tertiary center will be quenched by this hydrogen radical from this tributyl tinhydride. So these are the this is the major product. Option C will be the major product in this reaction. So that were the 10 questions of option. So 10 questions of week 7 assignment. So in the first question, we have seen this how DBU is helping in isomerization of double bond as well as the formation of new 5-membered ring. Then in the second question, we have seen how Friedel-Crafts acylation is taking place with the help of this MSOH and this methane sulfonic acid and P2O5. Then in the next question, we have seen how the oxidation of this NH2 and OH2 quinone is taking place with FeCl3, and then this reduction by using SO2. And then we have seen MCPBA epoxidation and this titanium isopropoxide mediated opening of the epoxide. And then this activation of carboxylic acid into corresponding acid chloride and diisomethane formation, and carbon through carbene the new ring is getting formed. Then in the next question, we have seen the mechanism for Mitsunobu reaction, and then this hydroboration oxidation we have discussed. And then how samarium iodide is helping. Samarium iodide is actually a one electron donor, and this is an electron mediated ring closing reaction, cyclization reaction. And then we have seen this Darsen's reaction and its mechanism, and then this free radical cyclization followed by ring opening, tandem free radical cyclization and ring opening to get this bicyclic compound. So, with that, our discussion on the assignment questions are over. So, now let us move on to the discussion on the week 7 lectures. So, today I have not included any content in the lecture that we will have the discussion. I have just included the structure of that particular natural product on which based on which the discussion was about. So the first lecture of week 9 lectures were lecture 40 on Swain Sonin, which is a natural product based on which the discussion was about. So in that lecture, we have seen the application of stereo-selective construction of tetrahydropyran in the racemic total synthesis of Swain Sonin by Mukai and total synthesis of minus Swain Sonin by Pearson using simple organic reaction with short and efficient sequences. So this Swainsonine is isolated from the fungus Rhizoctonia leguminocola, Swainsona canescens, and Metarrhizum anisoplay. And it is having three hydroxyl group, and this is an indolizidine alkaloid, and the biological activity includes mannose inhibitor and anti-cancer drug. So other non-acid sugar inhibitors are homoalexine, homoaustralin, alexine, and australin. So we have seen four total synthesis for this particular natural product, three of which were from sugar, and the last one was not from sugar. So the first total synthesis which we saw the discussion was Hashimoto's total synthesis, which was completed in 1985, starting from D-mannose, which is protected with acetone to get mannose diacetonide, and the key reaction in that synthesis was nucleophilic opening of epoxide followed by the formation of six-membered lactam in one pot. And he could complete that reaction in 12 linear steps with 4% of overall yield. Then the next total synthesis was Pearson's total synthesis for the Swainsonin, which was published in 1996, starting from another sugar that is D-erythrose. And there the key reaction was sharpless asymmetric dihydroxylation and one-port reduction of azide and cyclization to substituted pyrrolidine. And there he took 12 linear steps to complete the total synthesis in 19 with 90.6 percentage of overall yield. Then the next total synthesis was from Char's group, that was completed in 1989, again starting from D-erythrose. And there the key reactions were intramolecular 1,3 dipolar cycloaddition, stereoselective reduction, imine and cyclization, that is by the extrusion of nitrogen, and one-port stereoselective hydroboration, reduction of lactam, and Wittig reaction. And this total synthesis was completed in 6 steps with 21 percentage of overall yield. Then we saw the one synthesis which was the formal synthesis of Swainsonin by Zhou's group, which was not from sugar, and this was published in 1995, where the key reactions were Akhmatovich rearrangement, sharpless asymmetric dihydroxylation, and the kinetic solution of alpha furfuryl amide. So the starting material was furfuryl, and this synthesis took almost 15 steps to complete the formal synthesis of Swainsonin. So the next lecture was lecture 41, that was about staurosporin, where we saw the application of intermolecular indole glycosylation in the total synthesis of staurosporin by Danishevsky. And this particular compound is isolated from Omura from Streptomyces staurocypus in 1977. As we can see, it is having two indoles and one isointolinone in the northern hemisphere and another sugar moiety in the southern hemisphere. So its biological activity involves nanomolar inhibition of protein kinase C, and it acts as a potential anti-proliferative agent. So for this molecule we have seen, I think, two total synthesis. First one was Danishevsky synthesis, which is the first total synthesis for staurosporin, which was completed in 1995. Major synthetic challenges faced by these groups are the attachment of glycoside bonds to each of the indole nitrogen, Then their strategy for the containment of the future N-methyl and O-methyl moieties in a cyclic framework, which provide chemical protection and offer stereochemical guidance for the intermolecular indole glycosylation. So the starting material used were dibromomalamide and L-glucose. So they took almost 28 steps from L-glucol and they completed this total synthesis with 0.43 percentage of overall yield. Now, in John Wood's total synthesis, which was completed in 1996, it was an efficient divergent synthesis of pyranosylated indolocarboxyls via a common intermediate, and he took 13 steps from methyl 2 diazo-3-oxobutyrate, where we came across Moffat oxidation, then tandem 3312 rearrangement protocol using R-1 nonene triol as the source of symmetry, and they employed a successful ring expansion strategy to form the common intermediate, and from it completed the total synthesis of saurosporin. And they took almost 13 steps, and they could complete the total synthesis, and they got an overall yield of 9.61 percentage. Then the next total synthesis was about manzamine A. This is the structure of manzamine A, where we saw the application of De-Mayo reaction, Pictet-Spengler reaction, Rutro-Manich fragmentation, and Manich reaction in the total synthesis of this manzamine A. So this manzamine A was the first alkaloid isolated from the marine Okinawa sponge in 1986. And in 1986, Higa et al. And others isolated and confirmed the structure of manzamine A from marine Okinawa sponge haliclone. At present, more than 100 manzamine alkaloids have been isolated from over 16 species of marine sponges belonging to 8 different families. So the natural manzamine alkaloids, manzamine A N oxide, and 8-hydroxymanzamine exhibit potential anti-malarial effects. These groups of alkaloids have exhibited diverse pharmacological activities like anti-cancer, anti-malarial, anti-leishmanial, anti-Alzheimer's, antibacterial, and antifungal properties. So in 1988, Wingler et al. First reported the total synthesis of manzamine A. And in Wingler's total synthesis, the major key reactions were Pictet-Spengler reaction, Ritro-Manich reaction, intramolecular Manich reaction, intramolecular photocycloaddition, and the starting material was the corresponding pyridine derivative and one for butadiene. So that was about the discussion on manzamine A. Then the next discussion was about progesterone, where we have seen the application of Stock-Eschenmoser's hypothesis of biomimetic polyolefinic cyclizations in the total synthesis of steroid progesterone. So the basic skeleton of steroids is having four six-membered rings, three six-membered rings and one five-membered rings. And in most cases, there are two angular methyl groups, one at the C10 position and other at the C13 positions. And some of the examples of the steroids involves cholesterol, ergosterol, provitamin D3, cortisol, testosterone, norgesterol, progesterone, estrone, cholic acids, cholestanol, and the substituents are on the same side as these two angular methyl groups are beta substituents. So then we have seen the terpene biosynthesis, and depending on the number of carbons, if C10 carbons are there, we will call it monoterpenes, which are derived from geraniols. C15 number of carbons sesquiterpene, which are derived from farnesol. 20 carbons diterpenes, geranyl, geraniol, and 30 carbons we call them steroids, and they are derived from squalene. And for this terpenes, isoprene are the basic building blocks, and isoprene is existing in nature as its pyrophosphates, which are corresponding living groups, which are good living groups. So then we have seen some examples for monoterpenes like limonene, menthol, camphor, carbon, geraniol, citronellal, pinene, verbinol, and nopal. Then the Stokesian-Moser hypothesis was olefin geometry is preserved in the cyclization reaction. That is, trans-olefin leads to transfused ring junction. And then we have seen the biomimetic total synthesis of progesterone as well, and this is the corresponding structure of the progesterone. Then in the lecture 44, which was the discussion was about steroids and the application of markers degradation process in the total synthesis of steroids like diosgenin, progesterone, cortisone, and testosterone, where they have you how the development of industrial methods have came, that also we discussed as in a story. So I will briefly tell the story. So this diosgenin in drug discovery program, the year 1930s were considered as the decade of sex hormones. Molecular structures of male sex hormone, testosterone, female sex hormone, estrogen, and pregnancy hormone, progesterone, were determined and used as drugs. So much attention was focused on progesterone because of its medicinal properties in the treatment of menstrual disorder. Unfortunately, the high cost associated with progesterone restricted its use as a drug, and the cost of progesterone and other related steroids fell dramatically in 1940s with the creation of a Mexican company. So there comes this markers degradation process. So in 1938, Marker from Penn State University proposed the correct structure for diosgenin, which is a plant. The structure is given here, diosgenin, which is a plant steroid isolated from sarsaparilla. And the side chain of diosgenin was initially considered as inert, but Marker could cleave that using a clever reaction. In 1944, this Russell marker achieved the first practical synthesis of progesterone from this diosgenin. As the cost of this route is expensive, Marcus started looking at other sources to get this diosgenin directly. So, in his search for better source for diosgenin, he appointed several botanists and launched plant collection trips in southwestern states of America. This low-cost process of making progesterone became useful in making the anti-inflammatory drug cortisone, which is also given here. In 1941, while going through a botany textbook, he saw a picture of Dioscorea that grows in Mexico only, and the root of this plant weighs about 100 kgs. In 1942, he went to Mexico by bus and took two bags with large roots of this plant and returned. Unfortunately, it was stolen during the bus trip itself. He bribed a policeman and recovered a 50-pound root to Penn State University. And back at the Penn State, he could isolate diosgenin in satisfactory yield from this root. As this research program was funded by Park Davis, he approached them to commercialize this process. Not only they refused, other pharma companies also refused. Then he went to Mexico again, collected 10 tons of this root and talked to a local scale extractor and asked him to extract the root with alcohol and give the syrup. He gave him one third of the syrup and came to New York with the remaining. That syrup he converted into 80 kg of progesterone, and he sold 1 gram of progesterone for $80. He decided to form a company then to start this manufacturing, and he thought the best place to do would be Mexico, where the raw material diosgenin was available. He found two entrepreneurs, Somlo and Lehman, and together they signed an agreement to form a new company called Syntex. In 1944, Marker then resigned from Penn State University and moved to Syntex. Now they could sell progesterone for $50 per gram. In 1945, there was a dispute in profit shares, and Marker left the Syntex company. As he himself was doing the whole work with coding the reagents, the other two couldn't repeat this process. Marker moved out in 1946 and started a new company, Botanica Mex. He was with this company until retirement. Meanwhile, Syntex was looking for someone who will continue this work. They found George Rosenglass, who received this work, and Syntex again started selling progesterone. He extended this work to other steroids like testosterone also. Then Syntex also later collaborated with Professor Carl DeJersey. He succeeded in converting diosgenin to cortisone. Existing Merck process took almost 36 steps to make cortisone. Upjohn and Co. invented a new microbiological process to oxidize progesterone, and the product could be easily converted into progesterone. So they developed a 6 steps from this diosgenin to progesterone, and they have also developed this 16 dpa to cortisone and 16 dpa to testosterone. So this was the industrial method which was developed for the synthesis of this highly demanded steroids. So now I'll give you some time to go through these lecture contents. Then we will have a discussion on the some of the reactions that we discussed today. So, first we will be discussing this Collins reagent, that is basically this dipyridine chromium 6 oxide, and this can be prepared from this pyridine and chromium trioxide in DCM at 25 degrees Celsius. We will be getting this dipyridine chromium 6 oxide. So, what is its reaction, what is its use is that it will convert this corresponding alcohol into aldehyde, and the mechanism is like this oxygen lone pair will attack this chromium center to form this intermediate, and then this proton will be taken by one of the oxygen attached to this chromium, and here it will form a double bond. So this species will be forming. Then this, since it is under resonance condition with this nitro group, it will form this stabilized structure, and again this one other hydrogen will be taken by this oxygen to give this intermediate, and then this bond will be shifted to here, and this bond will be shifted to here to get this aldehyde and this pyridine and this corresponding alcohol as the chromyl alcohol as the byproducts. So in this way, this Collins reagent is used for the conversion of this alcohol into corresponding aldehydes. Now, the next reaction which we saw was Akhmatovich reaction or Asa-Akhmatovich reaction, where the six-membered ring is getting five-membered ring is getting oxidized to form this six-membered ring. Or it could be either nitrogen analog, where we call it as Asa-Akhmatovich reaction. So the mechanism is like this. First, NBS will form this bromonium ion on this alkene, and it will create this bromonium ion. Then methanol OMe will be attacking this bromonium ion, and it will open this bromonium ion to form bromine at this position and OMe at this position. Then again, in the presence of methanol, that OMe will attack at this carbon center, and this double bond will be shifted to here, and this halogen will be eliminated. So we will get this intermediate. Then under hydrolysis condition, this bond will be cleaved, and we will get this aldehyde, which will then undergo this ring closing to get this corresponding ring expand product as the major product. So that is the basic mechanism for Akhmatovich reaction. Then the next reaction is Sharpless asymmetric dihydroxylation, where this alkene on treatment with AD mix beta, water, and tertiary butanol will form this corresponding diol in an asymmetric fashion due to the chirality derived from this AD mix beta or AD mix alpha. So this is one of the examples. So depending on the catalyst, we will be getting different isomers. So if we are using this corresponding catalyst, we will get this diol, and if we are using this catalyst, we will be getting this corresponding diol. And this is the mechanism of this reaction. That is, first this alkene will coordinate with this osmium, this complex, and then water will be coming, and it will result in the formation of this corresponding diol. And in the second cycle, so this is the first cycle, that is water will coordinate, and this is correspondingly converted into this diol, and then again the remaining alkene will be converted into diol by passing through this cycle in this way. That is, this NaOCl will be converted into NaCl, which will convert this ligand back into its this position. It can again coordinate with this alkene, and then water will enter, and it will convert into this diol. So here this concept is that this AD mix alpha will be approaching from one particular phase, and AD mix beta will be approaching from one other particular phase, so that in both the case the diol formed will be having opposite stereochemistry, although it will be resulting in cis diols mostly. So that is Sharpless asymmetric dihydroxylation. Then the next reaction, which we already discussed previously also, is Fitzner-Moffat oxidation, where this alcohol is converted into corresponding ketone by using DCC, DMSO, and acid. So this is the mechanism of this Fitzner-Moffat oxidation. That is this pyridine will coordinate with this GCC, and it will form this, that is this nitrogen, this pyridinium ion, this proton will be taken by this, and then this oxygen will be attacked on this carbonyl carbon, which is electrophilic in nature. Then this oxygen lone pairs will coordinate with the sulfur of this DMSO, and again this pyridine will take up this one of the hydrogen from this methyl group present in sulfur, and then again this nitrogen will take the hydrogen from the oxygen out here, and then we will get the corresponding product after aldehyde after the elimination of this DMS. So this is the mechanism of this Fitzner-Moffat oxidation. This is basically a chemical reaction for the oxidation of primary and secondary alcohols to aldehydes and ketones respectively. So the oxidant is a combination of dimethyl sulfoxide and DMSO. So this dimethyl sulfide and urea, dicyclohexyl urea will be the byproduct. So the intermediary of a sulfonium group is involved, formed by the reaction between this DMSO and this um, carbodiamide. So this particular species is highly reactive and it is attacked by this alcohol. Then the rearrangement will give the alkoxysulfonium halide, which decomposes to give this dimethyl sulfide and this carbonyl compound. Now, the last reaction of today's discussion is Pictet-Spengler reaction. So, it is a chemical reaction in which the beta-aryl ethylamine, that is this compound, undergoes condensation with an aldehyde or ketone followed by ring closure. So, traditionally we will be using an acidic catalyst in protic solvent which was employed with heating, and it is considered as a special case of managed reaction which almost follow the similar reaction pathway. So the reaction mechanism occurs by first the formation of this iminium ion followed by the electrophilic addition at this third position. So first this iminium ion is formed and then electrophilic addition will take place at the third position in accordance with the expected nucleophilicity of indole to give the spirocycle. After the migration of this migrating group, deprotonation gives the product. So this is one of the possible mechanism, and whatever I told is another possible mechanism through the indole and then rearrangement. So here what is given is first the iminium ion formation and then the deprotonation to get this amino alcohol type of compound. Then again protonation of this hydroxyl group and elimination of this water molecule to get this iminium ion. And then deprotonation to get this Schiff's base. And then what will be happening? This bond will attack at this carbon center and this will go to here to get this corresponding ring close product. Then deprotonation will be giving this tetrahydroisoquinoline type of derivative. So this is known as Pictet-Spengler reaction. So I'll give you some time to go through these reactions which we discussed today. Then we will wind up today's session. Okay, so with this, we will be winding up today's session. I hope the discussion was helpful for you. If you have any queries or doubts, feel free to ask in the coming session, or you can post in the NPTL Swayam portal as well. So, thank you for listening. We will be continuing the session in the next class. Thank you. Thank you so much.